Works? Works? Okay. As well, there was the government people that were doing things, and they were basically trying to be sneaky. They weren't really using or reusing much of the code. So everybody wanted to keep a low profile. There was little reuse of code, and well, you might remember groups like 29A and computer viruses that were incredibly advanced at the level like Metamorph, computer viruses that were able to disassemble themselves and reassemble themselves, and it was just made for fun. They weren't actually trying to be especially nasty to antivirus. That was just a nice side effect. Most of them actually didn't even have malicious payloads. They were just had a message and everything, spreading some political thing or something. So that was the past. It was mostly handwritten, no libraries, no nothing. Like whenever there was some new variant, the guy just like adapted it to new OS or just discovered or thought of a new technique to hide itself or to stay resident in memory, hook some new interrupt, whatever. They just like wanted to evolve it a little bit. But like families were like 3 or 4 members to max. Or somebody else took the virus, disassembled it, and took a look and added a couple of new things. But they were very small families. And there were like really interesting cases like setmist from Zombie, like amazing virus, you know, manages to insert itself into an application by disassembling and reassembling itself into the flow. Just crazy stuff. And really nasty to disinfect too, basically. So, but it has changed nowadays. Nowadays, people started realizing that, you know, writing malware can actually make you money. You can create zombie networks where you actually can use them to send spam, to data mining for credit card numbers, launching DDoS attacks. Well, there has been a whole economy, underground economy developing on this. You can rent these computer resources. Basically, they have supercomputers at their disposal that they can rent and offer services on them, like distribution of stuff, hosting illegal websites. So these guys are making money, which in turn means that they can actually put money into developing new techniques and new resources. So the trends that we are seeing is this professionalization of malware. We're seeing all these families of banking trojans, spam bots, spyware, and where they actually start adding things and start modifying in a way that they create these families. The families arise from the fact that they made small modifications specifically targeting not being detected anymore by antivirus engines. So these guys have heavy economic constraints, and it's a very wild environment out there, which is very interesting from an economics point of view because there is no subsidies to keep companies running. Whatever is bad is going to die. Whatever is good is going to persist, and you will even see viruses fighting against each other. It's as wild as it gets, and so they will just try to reach as big as a user base as they can in order to, you know, harvest the resources of the computers. They want to, you know, make as much use of an exploit or a certain technique as they can for as little resources. So they will, you know, try to rebuild and build on top of that. They have their own development environments and libraries in order to build onto those techniques. And so they've moved to developing from assembler into more advanced languages, C, C++, where they have their own libraries, and they actually have release cycles. Like lots of worms have kill dates, where they will actually stop working, or they will download updates, or they will, you know, give pass to something newer that is going to supersede them in technology or fixing some bug. So there is like really a malware industry. So, and that presents problems when you look at antivirus signatures and they work. Because these guys nowadays, I mean, the thing for them is not being detected. And antivirus signatures are relatively primitive in that they are basically checksum based, which is not necessarily something you can blame them on them. I mean, antivirus have been a bit sleeping on the laurels for a long time because I mean, they didn't really need to invest on technology to detect because it was pretty easy. You know, you just got fast, you could check some and tell, hey, this is the same thing. But nowadays, there is like this influx of stuff that is released continuously. There's like tons, like hundreds, thousands of samples released in a day. And they really, because they need to see every single file in order to create signatures. And it's really easy to break them. It's a real problem for them. They really have to invest into more advanced technology. So this signature-based technology, basically, doing checksums of the files is limited in that respect. And it's brittle just because it's very easy to modify. I mean, in this case, we're not even looking at changing the application itself. You're just looking at changing the file. But the same application is changing the file, change some bytes, and some signatures already won't work on it. And it's very local, that within the same application, you can just change very specific locations, and it will still run. So illustratively, we could actually write a small Python script that would just get a known malware that is detected and modify it and create like just by modifying a byte at a time and creating lots of different files with different bytes modified, you will try to get something that still runs and is not detected. So you can even automate that process of generating different strands that are not detected by normal antivirus engines, which leads into something that we can actually call offline polyformism, where they can automate the whole process. They can actually get the updates from an antivirus vendor and then try to just batch or automate the process of finding a variant of that malware that is not detected by these signatures. And whenever it's done, they just release it. They can just start changing bytes randomly. They can actually recompile, and they can go into more advanced things like changing the obfuscation, changing the packers, reorganizing the binary, changing optimizations. We'll talk about that later, in order to make a bit of a different binary that they will release. And nowadays we serve online scanners like VirusTotal and some of the others out there that they get basically real-time feeds from the antivirus companies. You can even make a script that fetches it, like launches it to the service, waits for the result, you get the result, and then once it's not detected anymore by a given amount of antivirus engines, these guys run like 30 or 40, you can choose when to release the new piece of malware. So all automated, how nice. So it would be nice if you had some sort of technique in order to look at things at a higher level. So the combination of this automation with the current technology employed in antivirus signatures makes it kind of a bad combination. Just because antivirus really need to see the computer virus in order to generate a signature. And nowadays, like guys like, for instance, that write Storm, they don't even care about that. They just like constantly release a stream of different variants, and they will just release a different stream next day. So if it's detected in 24 hours, we don't care. We're in the new batch. It's like it's not relevant anymore. So, and there is lots of ways of achieving different variants of malware, not only just by changing the bytes, but nowadays even just by changing compiler settings, changing the optimization settings, would lead to certain structural modifications at the level of like bytecode, the actual assembler code change in the program, which obviously will make any signatures of it mostly useless because the actual bytes in the program change. Even the semantics still the same. So what people have been looking into are trying to automate the process and look at it a bit of a higher level, hopefully. And there are 4 common different approaches to this that have been actually tried. First, I'll try to discuss all of them and see which points they have in favor and which against them. First one will be behavioral classification. Basically, in this case, you see what the application does and try to work with that. And if you see an application that behaves similarly, you try to assume it's the same. So in this case, you would be actually able to tell, like getting a new sample from the wild, like your mail stream, whatever. You will be able to see whether it relates to anything you have in your database or no by behavior. So you don't need to wait an antivirus signature. You already know that, okay, this looks pretty similar in behavior to something really nasty that I have in my database. So let's stop it. Engrams and mperms, which is like fancy terms to refer basically to relatively advanced statistics you do at the code level. You basically look at the whole application at the code level and try to generate certain mathematical constructs, certain vectors that you would then compare and will try to tell you how close the code of one application is to another. This is, and has worked really well in some cases, but nowadays has very important limitations. We'll see them in a second. Basic block distance goes a little bit along the same lines as the previous one. It tries to work at a low level, at the basic block level of the application, which captures some features, but I tend to believe it forgets or misses really important ones. And then I'll move with what will be the main topic of this structural classification, which I believe is the strongest one because captures most of the semantics of the program, and in addition at different levels, so that if you miss some of the information, it's not it's all lost. You can still, like, some of the other information is going to contribute to tell you that this looks pretty bad, looks similar to something I already have. So now we're going to talk a little bit about behavioral classification. How does it work? Well, basically, it just listens to what happens when the virus runs. You can do this in a million different ways. You can hook APIs, you can do it at kernel level, look at syscalls, whatever. Like, as long as you get like a stream of things that happen in the system. So what they do, basically, they archive this as strings of API calls. And so whenever they get a new piece of malware, they will do the same process and get another stream, and then they will use techniques like Levenstein's distance, which basically gets two strings and calculates how many insertions, removals, or substitutions of these entries you need to do in order to make one into the other. So if you just need to switch a couple of them to make one identical to the other, well, it assumes it's basically the same stream of behavior to some extent. While if it takes a lot of time, if you get an application, whatever, Notepad, and you get a virus, the only thing they're going to have in common is probably GUI APIs, which really doesn't tell you much. And like Levenstein distance is going to be huge, and it's going to tell you this has nothing to do. So this is interesting. It doesn't care about certain things. It doesn't care how it runs, really, as long as it runs and you can capture it. You don't really care how many threads it runs. Can run in some problems with the threads if things get reordered, but most of the time there are certain patterns. You could even like specialize it per thread. And extracting the information is relatively easy, like applications that hook API calls, or you can do it with Oli debug, or scripting nowadays with all the Python frameworks that exist for debugging. You can automate the whole process. But it has problems. It has shortcomings. It actually has to run. You cannot just like get later to the system, dump the memory, and look at it, because you need to see it running. You need to see it doing the bad things in order to get this stream of things of happenings of API calls that you're going to use to classify it. And it's relatively weak in that you can obfuscate it by just adding random calls. You imagine you have you're creating a virus, and you have virus A, and then in virus B you have like lots of random API calls that don't do really anything useful. You can just open and close a file, but do it a million times. So that's going to add a lot of entries into these behavioral patterns that when they try to match them, it's not going to really look similar. Although it's garbage, it's not really useful, but it's really easy to obfuscate. You basically inject junk behavior on it, and it's really trivial to do. And for each variant, you can script this. So each variant is going to have a different junk inserted. So the signatures, the Levenstein's distance is going to be quite different. So it has some good things. It captures some of the semantics that we will see. The next two methods don't really capture semantics because they look too low. They basically look at the instruction level, while the behavior actually captures semantics of the application to some extent. Basically, here's the story as it's being told. It just goes through all that happens. Limitation is that only through all that happens. If there is a backdoor that will trigger a specific case, won't see that unless it actually happens to run. So it's a relatively good method with some shortcomings. Then moving to the next one, the n-grams and n-perms. The basic thing is you just get the disassembly of the program, and for the n-grams, you just count how many times a certain set of instructions appears in a basic block level or through the whole program. Basically just taking two pairs of instructions or triplets or whatever the n is, run it across all the program. And n-perms is very similar, but you don't take ordering into account. So if you have instructions like move, move, push, and push, move, move, those are going to be different n-grams because the ordering is different, but it's going to be the same n-perms because it's the same instructions, just different order. It's just going to give you different numbers. In some cases, it captures better the differences, because compilers, when they compile, they tend to do instruction reordering if you change a couple of things just for optimization reasons, like instruction scheduling. So the n-perms probably is a little bit more flexible. It's not going to fall for that. It's going to still find things similar, even they have been reordered, if the ordering didn't matter in that case. So basically, once you have this, you just create vectors, like big dimensional vectors with these numbers, with these counts of n-perms. And what you do, basically, is you do a dot product of these ones divided by the absolute value. What that means is that if they are very similar, the value is going to be close to 1, and if they are orthogonal, it's going to be 0. So, I mean, you're going to get all these numbers, and if all these numbers are pretty much the same, you're going to get two vectors that are pretty much like very close aligned, and the closer they are, the product is going to be closer to 1. The more divergent, up to like 90 degrees, like if there's like totally nothing to do, then the product will be 0. So it works for classifying stuff. And if you apply this to like long time, like 5-6 years ago, strands of malware like MyMails and MyDooms, where they were really not putting that much effort into the obfuscation. They were just adding a new feature, recompiling, same compiler settings, same everything. In those cases, this gives really good results. It classifies that family really well. But it has the problem that it's really easy to break, as we will see in a second. It's really fast. It's not localized because it looks at the whole binary, so that's some of the advantages. And the nperms is actually resilient to code reordering, mostly, and resilient against what?
You lost signal.
Oh, long time ago, or?
Oh no.
Oh, okay. I was like talking here for half an hour with no signal. Okay. So it's resilient against different kinds of modifications to the code, just because it abstracts a little bit, like the ordering. But it has problems, like the code motion. If you, depending on the window size you are looking of instructions, if you get beyond that, you can actually break that resilience. Average basic block is relatively small, and actually that's the case when, I mean, the smaller you get, the less general you get. Like the last point mentioned, like when n equals 1, you're looking at a basic instruction level, which that means that you're basically doing a histogram of the mnemonics of the program, which is even still works in quite some cases, not nowadays, not for like actual strands of malware. Still gives fairly interesting results though, and like for toy game, for toy play with malware. So it has shortcomings, and it's really easy to fool too. Well, as well, if you actually use different compiler settings, because that's gonna modify a lot or could potentially modify a lot of the instruction set that is used, or even change compilers, go from Visual C to GCC, something that has a slightly different optimization, has a slightly different weights about which mnemonics or which instructions to use, is going to produce a different, slightly different binary, which might break a little bit this thing. At the level of fooling it, we would then only need to insert large amounts of instructions that in different pieces of malware that don't correlate with each other. So it's a little bit like the junk in the behavioral classification, where you insert lots of things that do nothing, but actually make it difficult to match these two vectors. It would be similar here. We could add a lot of noise, a lot of instructions in one variant of the family, and another variant of the family, different set of instructions. And the point where like these two vectors will start having values that make them divergent, because this guy has like a lot of a certain combination, this guy has a lot of certain combination. So, and that is very easy to automate, because it doesn't even need to be code that gets executed. It can be executed. It can be code that is like, is referenced but never run, but it, it has like a really big bias at the level of the instructions that are used. So again, can be broken or made to perform poorly. And well, why it breaks is basically what I went through. You get that vectors misaligned and values increasingly close to 0. Then another approach would be the basic block distance, which is a bit funky to explain, although it uses some of the techniques we already saw, like the Levenstein distance, to calculate the difference. But in order to actually calculate the data that will be used to measure the distance, something called Bloom filters are used. And let's see if I can quickly explain this. Bloom filters basically are so that you have a set of hash functions. You will get every single basic block, feed it through that set of hash functions. The hash functions output will be between 0 and n, and you will have a vector in the end, where the entries on that vector are going to be set to 1 if you feed if the output of the hash function for that thing told you that that index should be set to 1. And in order to actually try to make this clearer, so if you have two different basic blocks and you send them through the hash functions, you will have k of these. The output of each hash function is going to be a number between 0 and n, which is the length of the vector. So you put the basic block, whatever measure, whatever numbers you extract from the basic block through the hash, it's going to tell you a number, and then you go to the vector, to that index, and set it to 1, right? So the idea is that if you feed two basic blocks through the hashes and give the same indices, then you're going to find indices in this vector in the same positions for both of them. So if you have 1s in all of them, then it's going to be that that vector is already there. It's kind of a fuzzy set probabilistical matching. So basically what you do is you feed a lot of data into it. It's going to set lots of ones for all the members that are into the set, and then you will get a new thing, and you want to know whether it's in the set or not. You run it through the same hashes, and if you find ones in all of the positions output from the hashes, then you know that that element is very likely to be in that set. So what they do is basically they feed basic blocks, and they basically generate a signature for the whole program, telling them, okay, this program has all these set of basic blocks. And then you get this vector, like relatively long vector. I mean, the longer it is, more specific it's going to be for every application. So then if you have two applications, well, another virus, you feed, you create another vector like this, and you do Levenson's distance between these two. If the basic blocks are pretty much the same, the actual vectors are going to be pretty close as well. So that's another way of going about it. It has some really good advantages, that it scales really well. Problems would be you have to be careful about the hash function, how it's implemented probabilistically, how likely it's to actually be unique for certain basic blocks, but as well it has to be a bit flexible, because you want it to be tolerant to certain easy modifications like instruction reordering, which happen really, really commonly. So it works, it's a good approach, but I see it more useful for non-malware environment, where people actually try to break it because it can be broken. Like heavy code modifications, like restructuring the code heavily or injecting lots of junk instructions will basically make the basic blocks look different enough that, again, these vectors would not really give you a good measure of distance. This is really interesting in-house if you have a really large collections of binaries that you need to classify. Like, I don't know, I've heard of these being used in Microsoft to classify their own binaries. So in that case, when you know that the binaries are not malicious and don't intentionally intend to break it, it actually works. It's a cute approach. And now we go into the one that I actually like, which is a structured classification. And as we will see, it relies on lots of different inputs from an application in order to construct the measure of what's going to be used for the similarity. It's based on BinDiff technology, which is one of our products, which basically can take two binaries and does a structural comparison. We'll actually go step by step into the structural comparison in a second, which basically looks at the binary at lots of different levels, trying to extract. I think from all these approaches is the actual one that gets closer to extracting the semantics, not really relying on instruction reordering. It doesn't even need to look at instructions. It tries to extract the semantic from all the relationships between functions. Maybe you can put it along the lines of what Google tries to do with PageRank and the web. You know, they look at the links. They don't necessarily look only at the text of the pages. They look at the relationships to decide what's important. This is a little bit similar. You look at the relationship between functions to try to say what's important, what's not, and what relates to another binary. So we have been using this and not only for malware, but for patch analysis, trying to find where things have been changed from Microsoft to Microsoft Patch. And and what they don't tell about what they have changed, which is really interesting. So in order to implement this, we need things. We need an unpacked executable, which this applies to any other approach. If you want to actually classify the malware, you need it to be unpacked. And actually that proves to be one of the hardest barriers of entry, like getting the actual malware unpacked. I mean, 80–90% of the malware out there is easy to unpack, but that 10% or 5% remaining tends to be harder and harder. So we need to disassemble the executable fully. For instance, behavioral analysis does not need that. It basically listens to whatever happens. We need to extract the flow graph. So we really need an involved disassembly process. We need to get as much as we can of it. We do some restructuring, some very silly optimizations at the level of removing unconditional branches, because everything that is unconditional, like if you have two basic blocks split, but there is just an arrow between them, you just collapse them because it doesn't really make sense logically. And it's basically running an optimization stage, trying to reduce everything to a canonical form so that we will actually run more generically into that. So if two programs, like one of them has not split a basic block and another has, just by collapsing every single instance we find, we're more likely to match these two basic blocks. So we try to extract all the call graph and flow graphs from an application. And then we run the matching actually in these graphs. So probably, I mean, if you have ever reverse engineered anything or thought of software engineering, I mean, it's pretty obvious that applications can be viewed as graphs. The call graph, the relationships between functions in a binary is a graph. You can express the calls like that. The functions within a binary, you can split them and represent them as a graph, where the edges represent the connections between the basic blocks, basically the true-false branches. Even the instructions you can represent as a graph, a really stupid and simple graph, which is basically a line, a sequential line, but you know, if you want to go all abstract, you can. So it's a graph. And as a quick example, well, this would be a very small application. You know, this is like an entry point, whatever. Probably the other one that is disconnected is some sort of a thread that is not directly referenced, and then the set of all applications. Usually, the leaves tend to be APIs, because well, we stop at that level. You know, we stop at the level that interacts with the operating system. So usually, the leaves are API calls, imported symbols from DLLs, or otherwise atomic functionality within the software. Then an example of a flow graph for a function would be this, which every node represents a sequential set of instructions, and the relationship between them represent conditional and unconditional branches, or switch case statements, or any other kind of flow, control flow structure. So we have this set of graphs. So the good thing is that these graphs capture a lot of the semantic of the program, of the meaning that the developer intended. It's difficult to keep the same meaning, changing a lot the application, because basically means they're going to be changing the calls and the order the calls are made. So that shifts a lot of the semantics, but moves them away. So the only things that actually change it, for instance, let's imagine that some guys change all the string operations to secure string operations. That's going to change the calls, but still within the context, two functions in the program, even the sub-functions are going to be different. They're string functions still, and the context upwards of those functions is going to be the same. So we can still match them. Adding logic to a function changes the flow graph. That's exactly the case when you fix a patch. Most of the times we see just an extra condition is added that goes to the end, exit returns an error, raises an exception, whatever. They detect that something is outside the boundaries. So, but still, those are very small changes, and most of the times we can actually tell that the function is the same, and actually that a basic block was added or removed. So again, semantics are kept very well. Compiler optimizations change a lot of the software. If you go really heavy, if you go like with heavy inline, like function inlining, loop unrolling, or the nastiest one starts to be like profiler guided optimization, where you basically instrument the binary, run it in test cases that are assumed to be typical test cases, and you get hot traces of where the application is most commonly running. And then you use all this information to recompile the binary, optimize to keep all these hot paths really close. So they are together in memory, so you need less pages in memory active. They are together in the cache of the processor, so it needs to hit less times the memory, which is really expensive. Really, really hardcore optimizations. So, but this basically makes the binary look like crap in IDA or any other disassembly. It's like you spreads the thing all over. Yet, still, the structure, if you can abstract from that, if your disassembler is good enough, the main structure is going to be pretty much similar. Some functions might be mangled together, but the basic block layout is going to be similar. And the one that is going to change most or only is the flow graph layout. The call graph layout doesn't really change that much for profile guided optimization. For inlining, it does, because some functions that might be present in a binary might be inlined and put inside another function. But still, that does not tend to be more than a small percentage of the application when it gets recompiled like that. So it does not affect that much, and that will be the critical cases. So pros of this is very resilient to all these modifications. None of them really break it, and because all of these contribute to it, it actually resets. If the flow graph is modified, well, we still have the call graph to look at. If the call graph is modified, we still have the other. If both are modified, well, we try to do as best as we can, and we usually do pretty okay. And so it's not localized at all. So you can release a new piece of malware with actually a whole new set of functionality, like an FTP server, somehow hanging out of a thread. But if the rest matches, you're going to still get 80%. if like that FTP server, whatever it is, or a spam bot part is like only 20% of the code. And it's not brittle because, well, as we've seen, you can do whatever you want on the binary, change it at the byte level. We don't even look at instructions for most of the time, so you can do whatever you want. You can add random garbage to it, no big deal. So the cons are that it's computationally quite intensive, so we don't have any hopes of having it running in any user machine, just because you need to do all this work. You need to have a database of graphs, and you need to be relatively clever how to go into matching those graphs. So it's not really suited for end user machine. Another drawback, but this applies to all the others as well. As I said, it requires an unpacked binary. And yeah, we need a full disassembly, and we need proper disassembly tools, which is arguable whether we have them nowadays. Either it's not too bad, but you know, I could rant about that. So, but how? I mean, if you're wondering how we actually do that, how we compare two graphs, it's actually not really that difficult. The problem itself, telling whether two graphs are isomorphic, that's like the math term for telling that two graphs are exactly identical. It's very, very hard, like the kind of thing you don't want to do or rely on as an algorithm. But the good thing is that the graphs they're working with have an extreme amount of information. We have on them, we have APIs and import names. We have libraries, we have entry points, we have exports that are other entry points. We have data, we have strings. So we can use all of these as fixed points. So if you have two pieces of malware, we can look for all these common things. We can look for APIs that they use that are in common. Data strings like URLs, like whatever, names, emails. And we can pinpoint these locations in the two binaries. So we have all these starting points. So it's not anymore a random graph matching problem. You have lots of starting points. The entry point is common. Every program has to have an entry point. So you can have a root edge, basically, a root node to some extent. So using all that actually gives us a really good way of anchoring two graphs to start matching them. And once we have that, I mean, the idea would be of matching this, that if we have two functions that share the context, ideally, if the sub-functions of k and k prime are the same, we would like to say that the functions are the same. That's basically how it works at the call graph level. So that if these two functions call exactly the same APIs and exactly the same order, but we don't need to run it, we're just looking at this assembly, we could assume, and this is the only instance in the whole application where these three APIs are used, we could assume that these two functions will be the same if it will be the same family. So, like mathematically, we would want to achieve the same result by like going from k, mapping it to the other binary and getting the children should give the same result as getting the children in the first one and mapping it to the second one. That would be the isomorphism, like the mathematical construct applied to this. But basically, in layman terms, basically means you want to look at the context and make sure that the context is the same. It's similar to what is done in some linguistics approach where you try to classify words in the language by looking at their context. If a word is used always with certain kind of nouns or certain kind of verbs, it's very likely to be the same. And you can actually cluster words by just that algorithm, by that mechanism. And that's pretty much the same. Look at the context. It has lots of information. So to do that, we need to actually tag all the functions with and assign them some sort of numbers that actually allows us to pinpoint them, whether they're singular or not. And in our case, we use a triplet, a three-dimensional vector, where the information that we encode is for every node. Looking at the call graph, every node is going to be a function. So we use as the components of the vector the number of nodes within the function, the number of basic blocks, the number of edges, connections between the basic blocks, and the out degree, the number of sub-functions called within that function. So once we have that, and we have all these funny numbers, all these vectors for all the functions in the binary, we start looking at the context, and already assuming that we already embedded all the information about APIs too. So let's imagine that we have the call graph, or subset of a call graph, a very simple program, where we have these values. The values are identical in both, but we have a problem in this case. In each instance, we have 642, 642. And 332, 332. So looking just at the vectors, we couldn't tell which one, whether can I use the mouse there? No. Whether this 332 is this one or this one. Obviously, if you look at the context, it's obvious. But if you would just be trying to look at the vectors, you wouldn't know whether just, by this number whether it's that one, or this one is the one on top or the second one. But if we just isolate ourselves and start looking at the context, in the case of the 762, the red node, which we know is the same because they are unique in the whole call graph, then we can just look at the context and we see that in the context they are unique, so we can match them. So once we have that information and embed it into the whole call graph, and I mean some edges in the one on the right, we already know, okay, those are matched, the other ones that are left are unique, so I can just continue the process and go to another context. Okay, these guys are the same, so I know how to match them, keep going. And now I only have like 2 functions left on match, which I know are the same. I mean, I know how to match because the signatures are unique and everything else is already matched. So by this progressive way of analyzing or going match in the malware, I can get a very good accurate view and like incremental view of how it actually maps one to the other. So then, once we have this, how we actually calculate a measure, a number that tells us whether it's similar or not. We would like to have water. Thanks. We like to have some sort of percentage measure, like 0%, 100%, whether the thing is similar to another. So we can do that by intersection. Thanks. We can have a. There you go. Much better. So by doing an intersection, if we have a set of functions in the whole binary that we know, well, in the 2 binaries that we know are the same, now what we can do is like get that intersection, the functions that are common for one binary and the other, and divide it by the number of functions in both binaries, like the union of both sets. So if the intersection is pretty close to the union, because we match almost everything, we're going to get pretty close to 1 or to 100%, however you calculate it. While if the intersection is 2 functions, that was the only thing you could match because it was the only relevant context, and the total number of functions is 200,000, obviously that's not going to be too similar. And the same if you have something like a much bigger binary than another, if you match like 100% or a really high amount of one of the small one into the big one, but not of the big one into the small one, that's not going to get a high percentage of matching. You will get an idea that is embedded, but you're not going to get 100% because there's lots of functions in the big one that weren't matching the small one. That's actually we are debating sometimes because in some cases we see a lot of use for that at the level of detecting whether some bad guys use something as a library in something else, but as well has the drawback that sometimes we don't want to know whether something is embedded. We just want to know whether something is close. So probably we should allow for different operation modes depending how you're looking at whatever you're looking, if it's not malware. So we basically do this measure for the call graph, the flow graph, and the instruction. We do all this graph matching, getting the similarities, doing the intersections, and the flow graph, call graph, and instructions. And then we have like 3 different values that tells us the difference, the similarities at different levels. So that's why it's resilient. You know, you can modify the flow graphs, but the call graph will still be pretty close most of the time. And then we basically do a weighted average of these values because we tend to attribute much more weight to the actual call graph. If the call graph is much similar but the instructions change, we don't really care that much about the instructions. Actually, I can tell funny stories where 2 different, same binary compiled for 2 different architectures was found to be like 99% similar. And if you had given a really big value to the instructions, that would have been lower. So it's really cool not looking at the instructions because then you can look at the same application compiled for different things and still get a really, like Warrior in malware, where you get compiled for different mobile phones. This was able to say that it was 90% similar without looking at the instructions, which is really cool. So we have problems like scaling. This is a computationally intensive algorithm. So the way we try to address it, we basically first we try to approximate, to just find good candidates to match. I mean, we have a large database. We have tried this with several thousand samples. We really don't want to do like all the pairs. That's not a good idea. So what we tend to do is just select, anyway, it doesn't make much sense trying to match something that is 100 functions against something that is like 5,000. Both can be malware, but not necessarily going to be too close together. One could be, typical Delphi monster, while another might be a very streamlined C whatever client for something. So we basically try to filter all things to get some sort of set that will make some sense size-wise and structure-wise. And once we have that, Then we try to actually do the detail matching, where we go to all this detail I just described, going to the call graphs, which is much more computationally intensive, but gives us the very definite similarity number or percentage. As well, we discard things that are too close. If things go beyond a certain threshold, we assume they're identical, and we don't even keep them in the database. Because it doesn't make much sense having like a collection with 20,000 things that are like 99% similar. Because if you get a new one, are you going to be matching against all those? Like, no, not really. It doesn't make much sense. You just want to keep a representative of that collection if it's that close to each other. So at the level of results in what we have been working with, actually the classification is not really the worst after doing these optimizations. Unpacking and disassembling are. Like unpacking, we're using a generic unpacking approach, which probably will be worth a talk on its own, and works fairly well. Has limitations, obviously. I mean, the nastier packers are really nasty. And disassembling takes a while, and we have to improve a lot on what IDA can do, which IDA tends to be the best available commercial solution for that. So it would be nice to have better disassembling engines, and we're working on that. At the level of parallelizing it, most of the components are parallelized. Basically, they are just VMs. We can run as many as we want. And the only thing that is not parallelized yet is the classification. It would be really nice to be able to run a classification for a single sample across multiple processes, instances, threads. But right now, it's something that we don't have yet. Halvard has some crazy ideas how to do it. We'll see how that goes. He says next spring, so probably that means 2012, though. So we'll see about that. How the system looks like, this is pretty much what we have built in-house, and some people are trying. We have a XML RPC server. On top of that, we have a web server GUI, so you can upload samples either from your scripts automated, or like a user can just go and upload stuff. And then we have like 3 different subsystems: the unpacking, just VMs, just fetching stuff from the queue and doing the unpacking if it's needed. Then disassembly and analysis, which will generate with all the disassembly and the data in order to diff things later. And the classification, which after filtering, we'd actually try to figure out how things are close, if they are, and then it would actually store everything into a similarity matrix. How the system looks like, or looked like some months ago, it looks a bit different nowadays. You basically, through the web interface, upload files, and you get a list of things, whether, I mean, this current status, here everything was already done, but it will tell you whether things are currently unpacking or whatever. Then you have the hashes of the files, descriptions, and how long it took to process each step. And if you actually want to see the results of the classification, if you go to the actual Java applet view of this, you get like a hierarchy of classification, like the closest things, the same families being clustered together, while the different ones tend to, in this case, probably either we were classifying the same strands of the same family, or that we just had like a threshold really low, because most of the time, if you have different families, they just show as separate clusters, totally separate clusters. But you can regulate that index of similarity where you want to split them, because it's something that some users might want. Some people might want really strict things at the level of, I want to know within this family how they split together into subfamilies, and others want to look, okay, I want to see of all my mail stream, which ones are bunkers and which ones are whatever, based on very, very rough structural properties. So, can you break these? We try to give it a lot of thought how to break it, and yeah, there are ways of making it really difficult to actually, it's not really breaking, it's actually making it really poor or degrading the performance of the comparison, because basically, I mean, at one level, we're capturing a lot. I can think of one way of capturing more semantics, but nothing that can be really done in the short term. I mean, the best way would be actually doing this kind of graph analysis at the data flow level. Because if you can actually capture the data patterns, the data modifications within a program, you're basically really capturing semantics. So, but that's for another day, I guess, because there's going to be some work. But of all the approaches I know, this is the one that will capture most of the semantics of the application. So it's difficult to think of breaking this without changing much of the semantics of the application. I've seen some cases where we wanted it too much to samples of the same family. When we look at them, is okay, they're in the same family, the same person kind of made them, but they're so different to some extent, even if it's just obfuscation, that it's almost hard to justify that they should be the same, because they actually changed. So it goes a little bit of how you wanna think about it, because if you change the semantics, If you change that much the call graph, well, it's not really the same application, right? So that's up for debate. But yeah, you can do certain level of obfuscation that makes the disassembly, trickles the disassembly first. That will be, if you break the disassembly, it breaks most of our, because it relies on that, most of our analysis. But we survive that pretty well. But you can use still obfuscation, like opaque predicates, like jumping into the middle of all the instructions. Junk code doesn't really do that much to us. It will be basically confusing the disassemblers, and there are different techniques to do that. But we have different assembling engines we can use nowadays, so we should be able to survive that pretty well. And yeah, I mean, the idea will be to get the attackers to implement and to put a lot of time into really advanced obfuscation techniques. One thing that was discussed, was mentioned to Halvar, and we just talked about, was the dispatcher way of where you basically would change a whole application, just having a single function where you will map every single API call. You will assign them a hash, some sort of number, and redirect everything through that. Basically, you end up flattening to some extent the whole call graph. You don't have that structure anymore. The idea will be looking something like this. Every single function goes through that dispatcher. Whenever you want to call some other function, so flattens the call graph. To that, I mean, definitely we lose this information. Although, well, if we have two samples with the same dispatcher structure, I mean, they're going to look flat both, so not really interesting. But the good thing is that we don't only rely on that. The flow graphs, the actual graph of every function, unless they are all of them very close to each other, which is relatively hard if it's a big application, you're going to have.
What about breaking function boundaries? Fooling IDA. So function A is not there anymore, or function B is not there. Like Microsoft put move ADI to EDI for hot patching, right?
Yeah.
It broke IDA 4.8, so he has to come up with 4.9.
Yeah.
So if you change every read instruction into pop EBX, jump EBX, if you change entry points.
We don't use IDA's function recognition stuff. We have our own for reasons like that. So. And as well, we don't use IDA's flow reconstruction code because it cannot handle like chunked, multi-chunk things and all this profile guide optimization. When you start sharing basic blocks between functions, IDA goes woo. So really, it's like goes crazy. So we have our own staff that basically reconstructs the flow and doesn't care whether things are the same or not. It's going to get all the functions and it's going to get all the stuff. So we know, we've been working a little bit with it, so we know what limitations it has. Still, there are limitations. There are ways you could break it, but I don't think at that level that it would be that bad. But well, give some people time and they will figure out the way. So at the level of functions, as long as there is distinctive functions, as long as you have like a big function or two big functions, the listener or the spam bot part or the spreading algorithm or the dropper that are significantly different from the rest of the functions, we will be able to match that to each other. We won't have the context, but we may still get a high percentage of matching. Definitely it will degrade it, but that's the good thing. It degrades more or less gracefully. It doesn't stop working at all. So that's a good part for it. So well, this will be the discussing on that. So yeah, it deteriorates, but doesn't really go into decay and totally. And as a last remark, which I seem I'm making a pretty good time after all, would be that the worst things for us are virtual CPUs, because that really removes a lot of the logic. Basically, the idea would be that you generate a software CPU and you compile your application for that software CPU architecture, and then your malware runs basically an emulator for that virtual CPU. And so you basically abstract that. In this assembly view, you only see the virtual CPU. The actual logic of the malware is running at a higher level. So from the assembly point of view, it doesn't really capture any semantics of the application. You just see it like, you basically see all the mnemonic resolution, all the register addressing, so it's really, really abstracted. So in order to overcome that, and well, things like Temida, which actually these CPUs change all the time, they are not the same. It's not like, if you figure out the way it's made, you can actually make something against it specifically. You would really have to make it generic because it changes all the time. It's like multiple architectures that CISC and RISC, and they're polymorphic in addition. So those guys have a lot of free time. And so that's difficult, just because it removes you from the semantics. And it's relatively easy to keep doing that by just recompiling or recreating the VM. So that's that stuff. But still, if there are some similarities between the VM, in one sample or another, it might still match something. But I would say that's one of the hardest challenges. So far, we haven't really been, we have seen samples packed with Temida and other things, but not really widespread. Like the Storm family usually uses a million tricks of their own, but I haven't seen one packed with a VM, as far as I know. But really trivial to do anyway. But that would be one of the hardest challenges, because removing the semantics.
Do you see a lot that use the dispatcher approach?
No, actually, not that we have seen. It's something that theoretically we have discussed and not really difficult to do, but I don't remember I've seen any. So I couldn't give you performance figures if it actually matches or not, but I would tend to think we do okay. So, more? I'm done. Any other questions?
You're unpacking with a virtual machine, right?
Mm-hmm.
So also you also have the dynamic
Yes.
stuff as well.
We can, and we thought of that, and that would be really cool, because you could yeah, you could embed, mainly for actually detecting when the unpacking is basically done, because if you start getting lots of APIs happening, it's like, oh, okay, now things are happening, but it's on the queue of things to do.
Data flow also within the virtual machine.
The what?
You can take the bytes and have data flow as well, I guess, in the virtual machine.
Yeah, we have total control over the VM. It's Python controlled, so I can do whatever I want. It's low, but so we can analyze, we can dump the memory, we have all the context, we have all the API, we can see all the kernels. So if things try to do nasty things, call syscall, I don't care, I can intercept everything. So that's a good thing. I mean, I have a syscall interceptor, so it can actually go straight to that. I don't care. I'll see it as if it will be API calls, all the same. So that's nice. I mean, the unpacking technology we have, I think, is pretty decent. But still, there are things that are really convoluted. Like I was saying, Storm, one of the things is like the simplest thing on earth, but it's really nasty. Is like a couple of samples we got like 2 weeks ago. Like at the entry point, they have a loop that does nothing. It's just 3 instructions, but it's done like 4 billion times. So in a normal CPU, that runs in under a second. But in a software emulator, it's not running under a second. So our main problem, actually, I mean, all our unpacking will run perfectly. It just takes long. So basically, we just have to optimize. Whenever nothing interesting is happening, try to run as close as native speed. And actually, the emulator we're using should be able to do several tens of millions of instructions per second. So that worst case scenario, we could optimize for those cases to run at emulator's native speed, because otherwise there's a lot of Python overhead. It should run within acceptable terms. I mean, we don't intend to do this real time. We have like something like 10, 15 minutes to get the classification done is acceptable for our current use of it. Maybe in the future we try to attack more problems with it and we want to faster. But hopefully we can just throw computers at it. That's a nice way of solving problems. Anything else?
Have you put any work into incorporating measures other than structural classification into the same, like generating a numerical framework that includes things like analysis of static of data in the actual binary, or things like n-grams or things like that, and combining them as both for comparison purposes as well as an overall better picture kind of thing?
No, we really haven't thought of that, because we consider quite some of them to be relatively weak or not contributing that much over what the graph approach, the structural approach could do. But I mean, I've played with histogram approach, n-gram approach, and it's useful in very constrained cases, maybe even shellcode analysis or things like that. But at the level of malware, I cannot see any big added value to it. I mean, that could be done, sure, and it might be useful even to be provided as an API for people to do their own things, sure. But we need to be a bit bigger to implement all that stuff. But I mean, it would be fun. I would love to do that.
As malware evolves and people start getting into better countermeasures, like something like just even simple data analysis would probably take you a long way when it comes to virtual CPUs and VMs. And
totally. If we could do the data analysis in a proper way, fast, that would be the way to go, because there's so many obfuscations that get totally destroyed by that. Like if you look at Temida, lots of the crap that it does, it's just tedious and it's not really difficult. It just takes you forever. And if you had a bit of exactly, that would be the biggest problem. If we could do it, that would be the greatest thing, because then we could actually move into this more real semantic thing. If you can actually abstract what is happening to the data, that's basically what the application is telling you. So doing diff on that would be awesome. But probably we need like new computers for that. Hopefully not. But Anybody else? No? Thank you. Hope you enjoyed it.